Okay, now we are going to start on our fourth step in the transportation planning four-step process, which is basically the trip assignment. In the previous steps, we calculated the number of trips generated and the trip distribution, how trips are going from production to attractions, and we came up with an OD matrix. Then in the third step, we did the mode choice, which is basically splitted the road users between using their own vehicles or using other modes of transportations like mass transit or subway or something else like that. Then now we want to assign those trips to the network. Okay, before we go into, so basically the step here, in this step, trip by travelers between origin and destinations are assigned to routes on the network. Okay, basically we need first to convert between person trips into vehicle trips. In order to do that, we need to estimate what we call VOR, vehicle occupancy rate. So the vehicle, we need to make a conversion between person trips to vehicle trips. That's number one. Number two, in this part we will focus on the shortest path assignment only, by the way. So there are several assignment methods. Okay, there are three approaches for assigning trips to routes, because the final product that we need to know on every link in the network how much traffic is expected to be there. So in order to do that, we have three different approaches. Okay, there are three. We have route divergence. That means between an origin to a destination. So that's an origin. This is a destination. We have one route, and we have alternative route 1, and we have another alternative route here, and we have another alternative route there, and we have other routes. So there are different routes, but there is different travel times, and there is different percentage for each of those routes. So the route diversion, in this approach, trips between an OD pair are assigned to alternative routes based on the relative route travel time, similar to the logit model, okay, used in mode choice. That means here we will use the percentage on route, okay, or trips, percentage trips on route I equal E to the power travel time minus travel time on route I divided by the summation for E to the power minus travel time on route I. I equal من 1 to n routes. يعني لو قلنا ده 1 2 3 4 5 we have 5 routes here. فبنعمل المعادلة دي، ومن هنا بنطلع percentage of trips، نسبة الرحلات اللي هتستخدمها اللي هتمشي على كل روت. تمام؟ طيب في طريقة تانية اللي هو استخدام shortest path، بمعنى أنا عندي origin وعندي destination، فاحنا بنفترض ان drivers will go on the shortest path only all or nothing. تمام؟ In this approach, all trips between an OD pair are assigned to the shortest path connecting between them. تمام؟ طبعا ده ما هوش realistic، الواقع الأوقع ده، بس this one is more difficult to solve. Shortest path assignment with capacity constraints. هنا it's different. هنا بقى هنشتغل بالshortest path، بس هناخد حاجة عندنا اسمها constraints as ايه، يعني لما الطريق ده يوصل للكباستي بتاعته الايه الدرايفرز يبتدوا يروحوا الالترناتيفز تانيين، واخد بالك كده and so on. واضح؟ اي سؤال يا شباب؟ طيب في حاجة مهمة جدا. There's another important point which is the wardrobe traffic assignment criteria. When we assign traffic to networks, we have two criteria for assignment. These were, suggested by Wardrobe, that's a scientist in the early 40s and 50s. The first one is user equilibrium. What is user equilibrium? Basically, it's a traffic assignment condition where no driver can reduce their travel time by shifting to another route between the same AOD pair. يعني احنا عندنا هنا ده OD origin وهنا ده destination وده هنا first route، ده هنا second route، third route، اوكي، fourth route. لو قلنا ان ده الترافل تايم هنا مثلا say اوكي ده كان 1 2 3 4 5 6 اوكي. لو واحد بيستخدم الروت، خليك معايا دي واحده، واحد مثلا say بيستخدم الروت ده اوكي، يبقى في different drivers assigned to different routes. In user equilibrium, this driver, okay, if he shifts to the other route, he's not going to improve their time. Maybe the distance on these routes are different, but the travel time on all these routes are almost the same. واضح؟ This is the idea of the traffic, the user equilibrium. Okay, this condition usually does not result in a minimum cost of travel, okay, for the system. الطريقه دي بالنسبه للسيستم اوفر اول ما بتديلكش ده يعني ده اوبتيمم فور ذا سيستم، بس اتس اوبتيمم فور ذا درايفرز. تمام. عموما دي الطريقه اللي هي المثلى لو احنا بنعمل موديلنج لاربن ترانسبورتيشن نتوركس. لكن في طريقه تانية اسمها سيستم اوبتيمم. سيستم اوبتيمم okay is a traffic assignment condition where the total travel time okay for the system is minimum. بمعنى هنا يا شباب we are focusing just on one OD pair، هنا we are focusing on the entire system. في عندي origin destination، هنا في origin destinations between different points. تمام. ف we are not focusing just on one OD pair. okay. هنا we are trying to assign the traffic in a way that will minimize the cost or will minimize the travel time. Okay. طبعا the system optimum it's not expected to result in a user equilibrium. Okay. Also it requires that each driver should follow prescribed route. يعني هنا الدرايفرز عشان يروح من هنا لهنا ممكن من مصلحته الشخصيه ان هو يمشي كده. Okay, if he is looking for his best route for this traveler, that's the best route for him. But for the system wise, it might be optimum to go this way. That means drivers are prescribed, are told, go this route, don't go this route. Okay. Okay, so what is the system optimum useful for? It's suitable for fleet management. يعني لو في عندك اسطول من الشاحنات وبتعمل له assignment، اوكي، بيبقى احنا بنعمل assignment according to the system optimum. لان الدرايفر you can ask the driver okay take that route and go this way, but road users you cannot say that. They have the choice to select which route and which alternative between their in their trips. Clear? طيب. First of all, let's calculate this. Let's discuss the shortest path algorithm. Okay, the shortest path algorithm, which you are gonna study next semester in the operation research course, it's basically to find the shortest path between an A and J. That's origin, for example, A, and that's a destination. So there is a labeling algorithm that will give us the shortest path to this destination. So what we do, we calculate the shortest path, okay, and we generate, what we call the shortest path tree, which is basically for each origin we build a shortest path tree, which is basically the shortest distance to all destinations in the network, like this one. So this is basically the shortest path tree for A. That's A, and these are the shortest path, shortest routes to all destination in the network. Then after that, we start assigning traffic. Okay. After identifying the shortest path for each OD pair, trips are assigned to the routes. Okay, and traffic volumes on the links in the network is calculated as following: summation travel over time, travel between for OD or trips for the OD, multiply xij for OD. Xij OD equal 1 if that link ij belongs to the route between OD. To better understand it, let's look at this figure, okay? And that's the link volumes in the example. Let me just make this little bit bigger, okay? And let's, for example, see what, the volume on link EF. Link EF serving volume from A to E, okay, from B to E. So each color of these, so that's EF or FE. So we have for OD pair AJ, this volume is going there, is going through that link. PE, this volume is going through it. FE, this volume is going. DE, D to E, that's the blue line. That's volume. So the total volume on that link is basically the sum of all these volumes. Okay? So this way, with this traffic assignment approach, we can determine the volumes on each link. Okay? Of course, this is not the optimum way of making traffic trip assignments, okay, but that's an easy approach to start with, so that could be a starting point. Any questions so far? Okay, so this is basically the all or nothing approach, okay, and as we mentioned, in the all or nothing we resulted in this situation, which is basically assigning all the trips. But as you can see, there are other trips or other links that almost empty, and this is not a realistic approach, or that's not what happens in reality. For example, the traffic coming from A, instead of going through this bottleneck, can use this approach. Okay, the travel time here is 1, 2, 3. So using this approach is basically 6 units of travel time, and here it's 7 units. But this will create a traffic jam, and the travel time, the actual travel time on that link will be much higher than 1. Okay, so basically travelers will shift to the other alternatives. Tamam? And and so on. Any questions? So the all or nothing is basically one of the approaches. Here, for example, say that we will introduce the capacity restraint method, which takes into consideration such phenomena. That means it takes into consideration that there is no traffic jams generated, or number of travelers exceeds the capacity of the link. So basically, the capacity restrained assignment method, it takes into account the volume on the link. And in this way, we don't use the all or nothing. We use incremental approach. That means we load the network in a stepwise. We don't put all the traffic like here, for example. We do it in increments. The trips are assigned in maybe 10% stepwise, in steps. يعني يا شباب في الطريقة التانية احنا بنعمل الاساينمنت على مراحل وبعد كده بنحسب الترافل تايم. طبعا في اول مرحلة بيكون الفوليوم زيرو, so it's going to be free flow. Once the volume start building up on the link, the travel time here will increase, the shortest path will change, and the volume will start being assigned to other links. واضح؟ دي معادلة انتوا هتاخدوها في الترافيك انجينيرنج اللي هو actual travel time equals T0, which is basically the free flow travel time, multiplied by 1 plus 0.15 times V volume to capacity ratio to the power 4 here. Could be alpha, whatever يعني. تمام. Any questions so far? Okay. Actually, this is a generic form for the travel time, which is instead of having a 4 and so it's alpha and beta, and it varies from one facility to another facility. So here, for example, the alpha and beta for freeways, okay, alpha is 0.88 and beta is 9.5. For multi-lane highway, okay, these are the values. So the link travel time, this is the general form, and in order to accommodate different road types, we have these are guidelines, and this is provided, I think, by AASHTO for the capacity constraints. Any questions so far? Okay. Capacity restrained assignment method. After calculating the new link travel time in the first iteration, recalculate the OD travel time and then reassign the trips on the network. As I mentioned, it works into an incremental approach, and usually this approach, okay, yields a user equilibrium. Okay, it's not system or system equilibrium. System equilibrium and user equilibrium are almost the same, but system optimum is different. Any questions? Okay. This way, at this point, we end the fourth step, which is basically the trip assignment, and we conclude the four-step planning process. Any questions so far? Okay.